So this is the assignment 402 mixed practice review in MyOpenMath, and I'm going to work through these problems, hopefully answer any questions that you guys may have. Question number one says, force is one of the fundamental concepts in mechanics, and great care is needed to clarify any misunderstandings and avoid developing new misunderstandings. Choose all correct descriptions and properties of force below. And so you have some options here, and this is a multiple response question, so you can check all of the boxes, just 1, 2, 3, however many you think are correct. The first one says acceleration causes force. The next one says force is necessary to keep an object moving. Force is necessary to move an object at rest. And force is necessary to stop a moving object. Right off the bat, I know that if I want to move an object from rest, I do have to use a force. And the same thing is true if I want to stop an object. If I want to change the state of motion of an object, then I need a force applied to it. Okay, so again, that goes back to Newton's first law. An object in motion will remain in motion at constant velocity. An object at rest will remain at rest unless there's an external force acting on them. So you would have to have a force there to change the state of motion. Those are going to be the only two that you need to select here, just those two. Acceleration doesn't cause force, it's really the other way around. Forces cause acceleration. And then this, of course, you do not need force to keep an object moving. An object will move all by itself unless there's an external force stopping it. It will continue to move forever. This one says your iPhone is resting on your frictionless center console, blasting Taylor Swift's newest album while you drive to a friend's house for a physics study session as shown. A deer darts into the roadway in front of you, causing you to turn to the right suddenly to avoid hitting it, which describes the motion of your iPhone when you suddenly swerve. So if this is your phone and your car turns to the right, right now your phone and your car are both going forward, let's say at 40 miles per hour. If you suddenly turn, your phone has inertia as well. It's an object in motion. It will continue in motion with a constant velocity. That means same speed, same direction, which means if I turn, it's still going to be wanting to go forward based on this position of the car right now. When the car turns, though, that's not forward anymore. That is to the top of my screen. And so the option that shows that is this one here. It would move toward the driver's side if you were to suddenly turn to the right, because now your car is facing this way over here, and the phone wants to keep going that way. Okay, and so it would be this option right here. And again, this is because it is frictionless, it is an object in motion, it will continue in motion with a constant velocity until an external force acts on it. Number 3, a spaceship in frictionless deep space fires its engines for 3 seconds, which describes its motion at the end of the 3 seconds when the engines are turned off. Okay, again, deep space, that's telling me right away, no friction, no gravity, no external forces. The only force here is the engines on this spaceship, and if those engines are turned off, there are no longer any forces acting on the spaceship. And so that spaceship, which already fired its engines, is now moving. It's going to continue moving at a constant speed. Again, this goes back to Newton's first law. It will move at a constant speed. However fast it's going after those engines fire for 3 seconds, that's how fast it's going to go until there's another force acting on it. Part of the same question, this one says, assuming the spaceship began at rest at the reference point when the engines are fired for 3 seconds, which position time graph could show the motion of the spaceship after the engines are turned off? Again, position time graph, or rather, let's talk about this first. After the engines are turned off is what we just answered up here. We said it moves at a constant speed, and so now we need a position time graph that shows something moving at a constant speed. Again, for those first 3 seconds, it accelerated from rest, starting at the reference point. So now we're no longer at the reference point. Now we are moving at a constant speed away from the reference point. And so I'm going to select this graph here because on an xt graph, constant speed is a straight line. And so I do need to pick one with a straight line. I don't want to pick a horizontal line because that would mean I'm at rest. And I don't want to pick one that starts at the origin because that is the reference point. And again, this is 3 seconds after it was moving, so it's already moved away from that reference point. So this is the answer I'm going to select. The next question, number 4, says, according to the free body diagrams above, which of the objects could be moving to the right with a constant velocity? Again, any of these could be moving to the right. So let's start there. Okay, I cannot tell what direction an object is moving based on its free body diagram alone. I need more information than just arrows and numbers. If they tell me in the question, if they tell me that it's speeding up or slowing down, I can kind of ascertain from the diagram which one that might be, or which way it's going rather, based on the diagram, but you cannot tell which way they're moving with just the information we have. So any of them could be moving to the right. However, there's more to this. This wants to know which ones could be moving to the right with a constant velocity. And the only ones that can be moving with a constant velocity are free body diagrams that show balanced forces. That's going to be this first one here, 25 up, 25 down, 20 left, 20 right. Those are balanced vertically. They're balanced horizontally. They're balanced. That's A. And then this one here at C is also balanced. But B and D are not showing balanced forces, and although they could be moving to the right, they would not be doing so at a constant velocity. Number 5 says a 13 kilogram object is moving across a friction-free surface with a constant velocity of 6 meters per second. What is the net horizontal force needed to maintain this state of motion? Again, this may sound like a calculation. It's not. Okay, the amount of force needed to maintain that state of motion would be absolutely none at all, 0. Okay, you don't need force to keep things moving. If there aren't external forces slowing it down, like this one says, friction free, there is no friction, then you don't have to keep pushing it. If it's already moving at 6 meters per second, it will continue doing so forever, or until it encounters some kind of external force. It collides with something, it does encounter friction, whatever. Otherwise, it's an object in motion. It will continue in motion with constant velocity. All right, question number 6 says, a rock has a mass of 12 kilograms. A box has a mass of 24 kilograms. How many times more inertia does the box have than the rock? Again, inertia is directly related to mass. So if a box has twice as much mass, then the box also has twice as much inertia. And all you're doing is comparing these values. 24 is 2 times larger than 12. So that's how much more inertia the box has than the rock, twice as much. Question 7 says, a block is accelerating across the floor in this room. Which of the following free body diagrams could show the forces acting on the block? Select any and all that apply. Okay, so forces that would be acting on an object moving on a surface on Earth. We have to have gravity. Okay, this room, we're on Earth. So we have to have a downward force of gravity. We also have to have an upward force of support from the floor because it is sliding across the floor, and we need to have those forces balanced. Up and down should be the same length. There's only 2 diagrams. Let's go ahead and select them that show upward and downward forces balanced. That would be FG and FN on both of these diagrams. Let's see if these are both correct though. Okay, so again, all it says is the block is accelerating, which could show the forces acting on it. Either of these could be true. Okay, you could have these forces here. Maybe you're pushing it forward and friction's kind of going against you a little, or maybe it's already sliding across the floor to the left and friction's slowing it down. It doesn't really matter what's happening here. It could be either of these 2 diagrams. For some of the questions, including this one, there are video tutorials attached to the question, so look for text like this that tells you to click here, and you may be able to watch a video for any specific question. They don't all have it though. This is number 8. It says, what is the net force on the box if all the forces acting on it are shown below? Again, in this particular type of situation, you're going to need to get the total amount of force vertically and the total amount of force horizontally separately, and then you're going to add those vectors together. I have a pretty easy one on my example because I only have forces in the same direction. So I have 2 forces going down. I know I can add them together to get an even larger downward force. And then I also have 2 forces going to the right. So I'm going to add these head to tail. Okay, and I don't have numbers yet, so I'm just adding them. But these will be my 2 downward ones. These are my 2 that are to the right. Now, if mine weren't in the same direction, I would have to take that into account, and I would be adding things in opposite directions, meaning I would be subtracting. But I don't have to worry about that here. Okay, so let's go ahead and get my vertical ones first. 94.2 plus 86.8 gives me 181. Okay, and then in the rightward direction, I have 87.4 plus 71.5, and I get 158.9. So those are my horizontal and vertical net forces. That's how much down in total, that's how much to the right in total. But this is asking for the total net force. It doesn't want the horizontal net force. It doesn't want the vertical net force. It wants the resultant. And that is the hypotenuse of this right triangle that is formed. This is my resultant. If I'm going down and to the right, then it will be at a diagonal both down and to the right. So I know my direction, down and to the right. Now I just have to find the magnitude. And I do that with a squared plus b squared equals c squared. So let's do that. 181 squared plus 158.9 squared is going to equal c squared. So I need to take the square root of this value to get my hypotenuse as 240.85. And of course that will be in newtons. I'm not going to include a sign here. Okay, I know that this is down, but I don't include my direction with a sign whenever I'm working in 2 dimensions. Instead, I designate my direction with one of these arrows, and then I use an angle. Okay, so don't type a negative here, even if yours happen to be like down and to the left. Don't do it. Okay, this one says, what is the angle of that force as measured from the nearest axis? So it's asking us for the angle, and again, we typically draw that angle from the starting point. The first vector I drew was right here. So I drew this and then I added this to it. So this is the angle it is asking me about. And I can solve for my angle theta using sine, cosine, or tangent. And I can use any of the 3 because I actually know all 3 sides of this triangle. But this one is rounded, so I'm going to stick with these numbers that are not rounded values, and I'm going to use tangent. And I'm going to say that the tangent of my unknown angle theta is equal to, again this is TOA in SOHCAHTOA, is opposite over adjacent. Again, opposite over adjacent. And so the opposite side of my angle is this 158.9. The adjacent side to my angle is the 181. I didn't use the hypotenuse because it had all these decimals. So if I want to solve for theta, okay, when I isolate theta, I'm actually dividing by tangent on both sides. And so I would have theta equals, and this is where you use inverse tangent. Anytime you are solving for an angle, you will use the inverse tangent or arctan function. Same thing with your other ones too. If you had gone with sine or cosine, you would be using inverse sine or inverse cosine. Okay, so we're going to do that and do second tangent. That's how I get the inverse. I'm going to take my 158.9 divided by 181, and I get an angle of 41.28 if I round that. So 41.28 degrees. Question number 9 says the x component of a force vector is positive 2.5 newtons. The y component is positive 12.5 newtons. Assume the positive to be north and east. Okay, so again, I have 2 vectors that are both in the positive direction. My first one is the x component. So again, I have axes here. My positive direction is going to be this way and this way. But if I'm doing this, my x component 2.5, I'll draw a vector along this axis going in the positive direction, 2.5 newtons. And then I'm going to add to that my other component. My other component is upward, the y component, and I know it's upward because it's positive. And that y component is going in the positive direction along that y direction, and it's 12.5 newtons. Okay, so this again is what your resultant looks like. So we're going to determine the magnitude of this the same way we did this one, Pythagorean theorem, a squared plus b squared equals c squared. Okay, and I'm going to use my 12.5 and my 2.5. So let's do that. 12.5 squared plus 2.5 squared And again, that needs to be the square root because that's c squared. So square root of that value, and that is my hypotenuse. 12.75, if I round that, would be the magnitude. Okay, now we have to find the angle. And again, we're going to measure the angle here from the first vector that I drew. I'm going to use tangent again because I have my adjacent side and my opposite side. I can use this, but remember it has all these decimals. So to avoid the rounding error, I'm going to go ahead and say that the tangent of theta is equal to opposite is 12.5, adjacent is 2.5, and if I want to then solve for theta, that's where I have to use inverse tangent of 12.5 over 2.5, and that's equal to my angle. Okay, so let's go ahead and do that. And we get 78.69 degrees. Okay, degrees from what? Well, we measured it here, and you can kind of see these were my positive directions, north and east. So I'm in this northeast quadrant, if you will, but the angle is measured here. It's being measured from this axis, my east axis, and so you can either say you're due east if it was horizontal, it's not. We could be south of east if we were on the south side of this axis, we're not. Or we can be north of east, which is exactly where we are. We are north of the east axis by 78.69 degrees. So I'm going to go with north of east. Question 10. Question 10 says a student pushes an 18.1 kilogram lawnmower. The handle makes a 20-degree angle with the ground as shown by theta. Consider the rightward direction to be positive. If the magnitude of the frictional force is 60.9 newtons, what magnitude of force must the student apply to the lawnmower to accelerate it 2.09 meters per second squared to the left? Okay, so there's a lot of information here. We're ultimately trying to figure out how much force the student is applying, and the student is applying a force at an angle. When I draw my free body diagrams, I'm not going to include that angled force. Instead, I'm going to get the components of it. But once I find those components, or at least one of the components and the angle, I can use trig or Pythagorean theorem, depending on which method I go, to find this diagonal force. And again, that's what this wants, the student's applied force, and it's diagonal, so we'll be putting that in here in a minute. Okay, but again, we first need to get an idea of what forces are acting on this lawnmower. Okay, so here's my lawnmower. I know that I'm going to have this downward force that he's applying. He's applying both down, that's going to be the y component of his force, and he's applying a force this way. That's going to be the x component of his force because he's pushing at an angle. Okay, again, you can draw in that triangle that shows this, and you can get his y and x components here and then transfer them over to your diagram. Okay, if it had given us the amount of force that he applied. It actually doesn't tell us, so we actually can't solve for that yet, but it does, we do know that there are going to be forces here and here. Okay, I know that I'm going to have Fg also in the downward direction because we always have force of gravity downward. I know that there is a support force from the ground, Fn. My normal force will be upward. My lawnmower is not accelerating vertically, so I know that Fn will be equal and opposite to these two added together. My net force vertically will be 0. Therefore, this minus this will equal 0, or you can say that the magnitude of Fn will equal the magnitude of y plus the magnitude of Fg. Again, these two add up to be equal to that. Okay. Now, if I had values here, that might be helpful, but I don't. I could find Fg, which I'll do in a minute. The only other thing that we need to include is friction, because it says the magnitude of the frictional force, so it actually tells us our force of friction. And the force of friction is going to be 60.9 newtons. Okay, that's the only number it gives us in terms of forces. But it does give us some other information. I obviously know the angle is 20 degrees, which isn't super helpful yet, but it'll be helpful in a minute. Okay, I know the mass of the lawnmower, I could certainly use that down here, mass times gravity to get FG. But the most important thing that I know right now is that this lawnmower is accelerating 2.09 meters per second to the left, meaning that there's a net force here to the left that is creating that acceleration. Now, I can't find the net force without this piece from the diagram, but I can find it from this equation. F net equals m times a, because they gave us those. So let's go ahead and figure out what our net force is. This lawnmower has a mass of 18.1 and it has an acceleration of negative 2.09. Again, because it's to the left, I'm tacking a negative sign on in front of that. So that's mass times acceleration, 18.1 times negative 2.09, and we get a net force of negative 37.829. So F net equals negative 37.829. Okay, and that net force is horizontal. Again, vertically, we already said these are going to need to be equal and opposite. This lawnmower is just moving across the ground. It's not moving vertically, much less accelerating. So this net force means that this X force here is 37.829 newtons larger than this, because my net force is in that direction. Again, we can also write a net force equation and say that the net force in the x direction equals the forces to the left plus the forces to the right, and we can solve for it this way. My net force is negative 37.829. It is equal to, my force to the left is the x component that I drew here. Again, that's from this diagram here, since he's pushing both down and to the left. That's this one, plus my force to the right, and I have the value for that one. It's force of friction, but it's to the right, so it's a positive number right now. Okay, so if I want to determine what Fx is, I need to isolate this. I just need to subtract 60.9 from both sides. Okay, and that cancels this, and over here we're going to get an even bigger negative number, which makes sense because it needs to be bigger in magnitude than the friction was. Okay, so minus 60.9. And we get negative 98.729 newtons. So that would be the force, the x component. That, by the way, is not the answer. That's not the applied force. That's at an angle. We just found this piece, the x component. Okay, and so my x component was again equal to negative 98.729. Okay, now that we have that, we actually do have enough now to solve for what the student's applied force is. Because now that we know x and we know the angle, we can use some trigonometry to solve for a hypotenuse. I know the adjacent side to my angle, that's what we just found. That's this value here, negative 98.729. And I know the angle, so I can solve for the hypotenuse, which is the student's applied force, using cosine. And so I'm going to say, let me move this so you can see it, that the cosine of my angle, 20 degrees, equals adjacent, which is x, which is this. I'm going to drop the sign here, 98.729 over the hypotenuse, and that's the applied force. And I dropped the sign because all I'm looking for here is the magnitude of the force. Okay, I don't care about the direction. I can see that in the picture. It ultimately does matter, but I'm not going to calculate it with the direction in mind. I'm going to calculate it based on the numbers to get the magnitude. Okay, so if I want to solve for this, I can't do that if it's in the denominator here. So I'm going to multiply both sides by that applied force. Okay, and now I can move it to the other, or isolate it by moving this to the other side. So I'm going to divide both sides by cosine of 20. So you're going to end up with this 98.729 divided by cosine 20 degrees. Okay, and again, I didn't take the negative off of mine, but this is the magnitude, or rather, if you ignore the negative, 105.06.
Lawrence Keating, you were just in front reception. Please come back, please.
Okay, so again, this is the magnitude would be 105.06. That's the diagonal. That was this piece here, and that's what your answer should be. Okay, so 105.065. Okay, I could have rounded that more, but if I leave extra decimals, no harm. Okay, the second question says, if the length of the yard is 25 meters and the lawnmower is initially at rest, how long will it take the mower to accelerate the length of the yard? Okay, so this type of question is pretty similar to what you're going to see in your free response. So I know that I have a length of the yard, delta x, is 25. Now I also know that my lawnmower is being pushed to the left, so I know it's going to move to the left. It's actually negative 25 if you think about it, because he is pushing the lawnmower in the negative direction. Okay, so that'll be my displacement, negative 25. The initial velocity is 0. How long will it take to accelerate the length of the yard? The acceleration was given to us in the previous question. It's also negative because it's to the left, 2.09 meters per second squared, and we're trying to solve for time. Okay, and so you're going to solve for time using a kinematic equation. With these pieces of information, this is the most appropriate equation to use. Delta x equals VIT plus 1/2 AT squared, and we'll solve for t that way. My initial velocity is 0, so this whole bit here is going to be 0 in a minute, but I can plug the rest of it in. Negative 25 equals 1/2 times negative 2.09 t squared. Okay, so we're going to do half of negative 2.09, and then we're going to move that over here by division, because right now this is being multiplied. So the negative 25 will be divided by the negative 1.045. Those negatives will cancel. So really it's just 25 divided by 1.045, and we get 23.923 equals t squared. Again, this is t squared, not t. We need to take the square root of it. That would be my time. So let's go ahead and type that in, 4.89 seconds. All right, question 11. Number 11 says, a student attaches a rope to a 38 kilogram box and drags it to the left with a constant velocity of 1.27 meters per second. The tension in the rope is 225 newtons at an angle of 45.2 degrees to the ground. Okay, how much does the box weigh? Okay, well the weight of the box I don't even need the rest of this for, because weight is Fg. Fg is mass times gravitational acceleration. The mass is in the question, it's 38, so we can get the weight of the box without doing anything in terms of a diagram. 38 times 9.8 is going to give us our weight is 372.4. Technically it is a negative value, but when we ask how much something weighs, we don't typically think of a negative sign, but it will take it either way. Okay, but this is a downward force, so I'm going to go ahead and type the negative 372.4. The next piece says to find the x and y components of the applied tension force. Again, if you have a force applied at an angle, do this anyway. You need to. Okay, you need it for your diagrams, you need it to figure out what your net force is in the x and y direction, do it. Okay, so if you take a look at this one, you have a situation where you have this being pulled at an angle. That angle is 45.2 degrees. You know that the tension in the rope, so this diagonal, that's the rope, that's where your tension is going to be labeled, is 225 newtons, and you're trying to figure out what the x and y components are. So you're looking for how much of it is up, how much of it is over, okay, because you know you're pulling it both to the left and upward. So you're looking for the x and y components, and you're going to find them using sine and cosine. The x component is adjacent here, so again, when I look at my little device to remember this, a little mnemonic, SOHCAHTOA, because this is adjacent to my angle and I have the hypotenuse, I'm looking for adjacent in hypotenuse, that's in cosine. So to find this one, I'll use cosine, and I'm going to have, it ends up being 225 times cosine of 45.2 degrees. For my y, it is opposite my angle. Again, I still have the hypotenuse. I'm looking for the opposite side, opposite hypotenuse. That's here with sine. This one ends up being 225 times sine 45.2. Okay, so it's a very similar process for both of them. Let's go ahead and do the x component first. Again, check your mode, make sure you're in degree mode. 225 times cosine 45.2, again, gives me my x component as 158.54. Again, this technically, and it tells you to assume upward and rightward to be positive, this is to the left, so it should be a negative number. It is. Okay, but it should be a negative value for this one. We're not going to get a negative when we solve for it. You just need to look at the picture and realize, oh, that's going in the negative direction. My y component's going in the positive. It's up. Again, to do this one, it's 225 times sine 45.2, and we get 159.65. And again, these make sense that they're really close to each other because this angle is almost 45 degrees. Okay, so those are reasonable numbers. The next one says how much friction must be present. Okay, so friction would be another force that you would have in the horizontal direction. We didn't draw our forces, but basically on our free body diagram we have the x component of this force. We're going to have Fg. We're going to have the y component of this force. We're going to have Fn. Okay, and now it's telling us that we're going to have friction, or at least probably. And if we do, it's going to be in this direction. Okay, now the way I know if I have friction or not is by looking at either my net force or my acceleration, figuring out my net force from there, or I look for words like this, constant velocity. Guys, if you have a constant velocity, it means that your forces have to be balanced. Ff has to be equal and opposite to x in order for us to have a constant velocity. I already know the value for x. I found it right here, 154.54. So that is also the amount of friction present, except friction is going to the right. So it's going to be a positive 158.54 newtons. But you need a net force of 0 in order to have constant velocity. The last question, how much normal force must be present? Again, we already looked at this, but Fn and y are both upward. Fg is down, and again, y is up because he's pulling it at an upward angle. Okay, we already have the value for y. Again, it's right here, 159.65. We already figured out the other forces in the vertical are Fg and Fn, but we need to find Fg, and then we can find Fn. Fg is mass times gravitational acceleration. We actually did it up here. Okay, 372.4. So this one is 372.4 newtons. This y component is 159.65 newtons. And what I know about these forces vertically is that they need to be balanced. Fn plus y needs to equal 372.4 newtons. Because if they don't, then my box is no longer moving along the floor. It's going to be accelerating up or down. Okay, so because I know y, 159.65, and I know this, I can figure out how much this is going to be because these two together need to be this. So I'm just going to subtract 372.4 minus 159.65. And we get 212.7465. It keeps going. But that would be your normal force. And it is an upward force, so I'm not going to type the negative. 212.75 would be an appropriate way to round that. Question 12. Question 12 says, in a lab, a block weighing 78.4 newtons is attached to a spring scale, and both are pulled to the right on a horizontal surface as shown above. Friction between the block and the surface is negligible. What is the acceleration of the block when the scale reads 24 newtons? Okay, again, you've seen this question a few times now. We started with it in the last unit. Okay, but we know that we have forces acting on this block. There is no friction, so really this block has just this force that's being applied through the spring scale, and it tells us what it is because it says the scale reads 24 newtons. So they tell us how much force is being applied to the left. I also know that I have Fg and I have Fn, and that these are equal and opposite to each other. And that may or may not be handy for me to know, but I'll go ahead and label them anyway. I'm not going to label any friction because it says there isn't any. Okay, so what is the acceleration of the block? Again, I can find acceleration with F net equals ma, or with kinematic equations. In this particular example, I'm going to use F net equals ma because I don't have any information to use my kinematic equations.
I had a catering order up front from local table. If someone could come up and receive it. Thank you.
All right. So my net force is going to be just this 24 newtons. There's nothing else happening horizontally. It's equal to the mass, which is not in the question. So we need to get the mass before we can get the acceleration. They gave us the block's weight. Okay, so there is a little extra step in here. Before I can put the number in, I can't put 78.4. That's not a mass. I need to use my weight equation, Fg equals mg. This time they gave me the Fg. It's 78.4. It's equal to mass times my gravitational acceleration. So you're just going to solve for mass. Dividing 78.4 by 9.8 will give you your mass of 8. Okay, so the mass of this object is 8 times A. So 24 equals 8 times A. Of course, A, when I divide both sides by 8, 24 divided by 8 is going to be 3. My unit will be meters per second, or meters per second squared. Second question, if the block is initially at rest and experiences this acceleration for 2.3 seconds, how fast will it be moving at the end of this time? So we just found an acceleration, 3 meters per second squared. They are now giving us some other pieces of information, like the fact that our initial velocity was 0, and that this acceleration occurred for 2.3 seconds. And they're asking us, how fast will it be moving at the end of this time? So we're looking for VF. Okay, this is a situation where you're using kinematic equations. If I ask you for time, if I ask you for final velocity, how fast it's going at the end, how far it has traveled, any of those other variables, you're going to have to use a kinematic equation. Acceleration is the thing that connects these two units to each other. It's here in F net equals ma, and of course it's in all of your kinematic equations. Well, except for the last one. So if we take a look at this and these variables, you look at your equations, this is the one you're going to want to use. VF equals VI plus A times T. Okay, and if we substitute in, VF is equal to 0 plus 3 times 2.3. So that's all you're going to do is 3 times 2.3, and that will give us our final answer. Our final velocity should be 6.9 meters per second. Question number 13. A kid riding a bike with a total mass of 34.7 kilograms is moving at 8.6 meters per second when he stops pedaling and coasts to a stop due to friction. If the coefficient of friction between the bike tire and pavement is 0.73, what is the stopping distance for the kid bike system? Okay, so there's a lot of information here. Ultimately, stopping distance, that tells me right off the bat I have to use kinematic equations. But if I don't know the acceleration, I'm probably going to need to use the force information to find it. Okay, and it doesn't appear that I have that here. But if I want stopping distance, that's ultimately going to be kinematic equations. So, forces, let's look at that first. I have a bike. The bike is moving at 8.6 meters per second, and he stops pedaling and comes to a stop due to friction. So he's no longer pedaling. The only force acting on him as he coasts along now, his net force, is his force of friction, because he's not pedaling forward. He does still, of course, have the support force from the road, Fn, and the force of gravity acting on him due to Earth's gravitational field. These are equal and opposite because his bike is not accelerating up or down. So that's your free body diagram. My net force will be force of friction. And that's important if you take a look at the information you have. Okay, so they give us the coefficient of friction as 0.73. Okay, and so I can find force of friction if I have my coefficient and I have Fn. Now Fn I don't have a formula for, but I do have one for Fg, mass times gravitational field strength, or times 9.8. Is going to give me my Fg and therefore also Fn, because these have the same magnitude. So let's take the mass, 34.7, it's in the question. And let's go ahead and multiply it by 9.8 to get our weight and also our normal force. So that's Fn. It's also Fg, 340.06. Again, if I want to find Ff, I'm going to multiply that times my mu value, 0.73 from the question, and this is my force of friction. It's also my net force. So let's go ahead and write it out. So my force of friction and my net force, F net, is equal to negative 248.2438 newtons. And I'm labeling it negative because it's in the negative direction. Okay, so this is FF, but it's also F net because it's the only force that's not canceled out. It's the only horizontal force, period. Okay, so now I have my net force. From here, I can find acceleration because I already know the mass, and I know F net equals ma. So let's go ahead and plug this in. Negative 248.2438 equals, the mass in this question is 34.7 times A. So we're going to divide our number in our calculator by 34.7. And that's going to give me my acceleration, except that I don't have the negative sign on mine. I should have typed it, I didn't. But my acceleration is technically negative 7.154 meters per second squared. Again, he's coming to a stop. It should be a negative acceleration. That's not the answer either. So again, we had to use forces to get the acceleration so that we can now use kinematic equations. You're going to have questions like this. You're going to see it on your free response. Okay, so let's go ahead and take a look at what else we know besides acceleration. We know that the bike is initially moving at a velocity of 8.6 meters per second. That's in the question. We know that the final velocity is going to be 0 because it talks about it coasting to a stop, and it wants to know what the stopping distance is. How far does it travel until it stops? So we have A, VI, and VF. We're looking for delta X. We don't have the time. Could we find it? Sure. We don't need it though. We can solve for delta X using this equation. VF squared equals VI squared plus 2 times A times delta X. So that's what we're going to do is plug in there. This one's going to be 0. So 0 equals VI is 8.6 squared plus 2 times negative 7.154 times delta X. Okay, so let's go ahead and get 8.6 squared. And let's move it to the other side. So now we'll subtract it. Negative 73.96 equals, let's do 2 times this value, negative 14.308 times delta X. Okay, again, I want delta X by itself, so we're going to divide both sides by this negative 14.308. The negatives are going to cancel. So it ends up really just being 73.96 divided by 14.308, which is equal to 5.169. meters. So that would be the stopping distance. Question 14 says, a student pushes a 1.6 kilogram lawnmower across his yard by applying a 97 Newton force at a downward 27.6 degree angle measured from the horizontal as shown. Mu is 0.7. Solve for. Okay, again, you need to be able to do this. Okay, this is what you're going to be doing in the free response, basically. So, let's go ahead and get a clean sheet of paper. FG. Let's go ahead and just draw these on our free body diagram to get the practice. FG is going to be a downward force. FG is going to be equal to mass times gravitational acceleration, okay, which in this question my mass is 1.6, gravity is 9.8, so my weight of the lawnmower is 15.68 newtons. This lawnmower is very light. All right, so we have FG. Okay, let's go ahead and type it in here as well. It does tell us to include the direction here, so this is a downward force. I can see that in my diagram. I'm going to tack a negative sign on, negative 15.68. Fn. Okay, so there are other forces acting on here. So this guy's pushing the lawnmower. Let's add his forces real quick. He's pushing, and he's pushing both downward, and he's pushing to the right. So his x component is to the right, his y component is downward because his force ultimately looks like this. He's pushing that way, part of it is down, part of it is to the right, and here's the amount that he's pushing with. He's pushing with 97 newtons of force, and he's doing so at an angle that is 27.6 degrees measured from the horizontal. I drew my picture a little bit different. This is the same thing. Okay, that picture up there has it drawn this way instead. If you did that, that angle and that angle are congruent. Okay, but I'm just going to leave it like this since I already drew it. Okay, so 97 and this, I can now solve for these two pieces using some trig. I can find my x, I can find my y. So again, if you have something at an angle, do this first. Now, FG you can do at the beginning, that's okay, but don't do these other ones until you find the components because you're going to get it wrong. Fn is not equal to Fg here. So let's do, this one's going to be adjacent, so we're going to use cosine. We're going to do 97 times cosine 27.6, and that's going to give us 85.96. That is my x component. My y component is opposite my angle, opposite hypotenuse. I'm going to use sine 97 times sine 27.6 gives me this value, 44.94. That's my y value. Okay, so again, he's pushing both to the right and down. There's to the right, there's down, there's both of them, there's his resultant. Okay, but these are the ones I want to draw on my diagram. All right, so we've got those. His normal force, again, this lawnmower is not accelerating off of the ground. It's just going along the surface. So my vertical forces need to be balanced. This force here needs to be equal and opposite to both of these together, okay, in order to balance it out. So I just need to add these together, and that's going to be equal in magnitude to this. These, of course, are both negative technically, but again, when we do this, we're just getting the magnitude. All right, and we get 60.62 if we round it, and that is Fn. All right, so let's go ahead and fill that in. 60.62 newtons. That one's positive. Force of friction. Force of friction will go opposite the direction of his motion, so he's moving it to the right. The force of friction will be to the left. Force of friction we can solve for if we either knew the acceleration, we could use that to find the net force and then find this, or if we know mu and Fn. I know Fn, I just found it. Mu is in my question, it's 0.7. So we can just use this formula here and say that force of friction is equal to mu times normal force. So let's go ahead and do that. My normal force is already on my calculator screen. Let's multiply it by my coefficient of friction in the question, that is 0.7. And that gives me a force of friction of 42.433.8. It keeps going. But please look at the picture. This is in the negative direction. So you're not going to get a negative number. You have to identify it as being negative when you look at that diagram. Negative 42.43 newtons. Now that we have that, we can find acceleration. Okay, again, let me go ahead and fill this one in. 42.43.
Pardon this interruption. Olivia Kate, I need you to move your vehicle immediately out of the van parking lot. Olivia Kate, please move your vehicle.
All right. So again, acceleration is due to net force. So we're going to go back to this. F net equals ma. We don't have any other information. There's nothing about kinematics here. You're just going to go back to this diagram. If you have all the forces, you can see the net force. The mass was in the question. We can find acceleration. The net force, again, is going to be horizontal. These are all balanced. So it is the sum of these forces, keeping in mind that this one is a negative number. So it's really subtraction. So it's going to be the 85.96 that we got up here plus negative 42.43. Okay, and again, that's really subtraction. So I get 43.53 if I round that, but that's my net force. That's not my answer. We're now going to take that 43.53 equals, the mass is in the question, 1.6 times A. If I wanted to solve for A, I need to divide by 1.6. And I get this, 27.205. Question 15. Consider a rocket being launched into space as in the photo below. If we call the thrust lifting the rocket the upward reaction force, which of the following is the action force pair to this reaction? Again, action-reaction force pairs, you need to have opposite directions. So if this is upward, we're looking for downward over here. But you also have to have it between the same two objects. So if this force pair is between the rocket and its combustion chamber, where the thrust is coming from, then we need the same two objects here. And so we don't want to include air. We don't want to include gravity. That's not part of this pair up here. We don't want to include the ground. We're just going to go with this, the force on the rocket fuel combustion products being pushed downward. Okay, question number 16 says, consider a tow truck towing a car. In the diagram below, two horizontal forces are shown for the tow truck and the car, forward force and backward pulling force on the truck, forward towing force and backward friction force on the car, which represents a force pair. Again, a force pair needs to be between the same two objects. So, for example, forward force of the car, or rather this truck, would be due to the tires pushing back on the road and the road in turn pushing forward on the tire. That's this forward force on the truck, but it's between the tires and the road. Okay, and so it's not between these other forces here. Same thing with the friction back here. Friction on the car is between the car's tires and the road. Again, the road, those forces are not going to be in between the car and the truck. The ones that are a force pair are the truck pulls on the car and the car is pulled by the truck, okay, or the car pulls back on the truck. Okay, but you have this towing force of the truck pulling the car forward, and you have this pulling force of the car pulling back against the truck. That is your force pair. Okay, so pulling and towing. If the tow truck pulls the car with a towing force of 1,200 newtons of tension to the left, causing both to accelerate from rest, how does the backward pulling force of tension compare? Okay, so again, it's talking about the towing force and the pulling force, which we just said is a force pair. So it should be equal and opposite. Newton's third law. It doesn't matter, by the way, that the truck is towing the car. Okay, that is still a force pair. They're still equal and opposite. It doesn't matter that it's going in one direction or accelerating, to the left. Doesn't matter. Okay, it is still a force pair. All right, this one, number 17, says, suppose you exert 350 newtons of force on a 19.7 kilogram crate and push it across the kitchen floor at a constant velocity. What is the force of friction between the crate and the floor? Again, these words, constant velocity, tell me I have balanced forces. So if I'm pushing with 350 newtons, so is friction, equal and opposite to me, so that I have a net force of 0. Friction would be negative 350, I'm positive 350. My net force is 0, and therefore I have constant velocity, which correctly describes the forces in this scenario. Okay, if the boy is pushing forward on the crate would push back on the boy, and it will be with an equal amount of force. Equal and opposite, there we go, third law. Question 18. A student pushes on a 12 kilogram desk with a force of 180 newtons. Consider one force to be the force of the student on the desk. What is the action-reaction pair to this force? Student pushes on a desk, desk pushes on a student. Again, it's that easy, force of the desk on the student. As a result of this force, both the student and the desk begin to accelerate at a rate of 8.9 meters per second squared. What is the magnitude of the force the desk exerts on the student? You just told me. Okay, this is a force pair. The student pushes the desk pushes the student. If the student pushes with 180, then the desk pushes also with 180. It does ask for the magnitude, so I don't need to include the negative sign. This one says, what is the magnitude of the force of friction between the desk and the floor? Okay, so this is asking about something outside of my force pair, an external force, and this is where I'm going to have to look at the other information they gave me. I know that I have two forces acting here. The force that is applied forward, which is 180 newtons, and this force of friction that's going against it. I know also that I have a net force that's causing acceleration. So I can find that net force, F net equals ma, okay, because I know the mass is 12 kilograms. That's in the first part of the question, and I know the acceleration is 8.9 meters per second squared. It's in the second part of the question, so we're going to multiply those together. 12 times 8.9, and we get a net force of 106.8. Okay, so that means this force is 106.8 newtons larger than this one. That's what the net force means. It is also the sum of my forces, 180 plus FF. Okay, that's going to be a negative number. That's the only way we get here. Okay, and I can see that mathematically as well if I just subtract 180 from both sides. Okay, 106.8 minus 180 is going to give me a negative number, specifically negative 73.2, but again, it only wants the magnitude, 73.2. Question 19, a semi-truck is driving down the road and the bug hits the windshield. Which one is true? This is similar to what was on your quiz. You're going to see it again, but the forces are equal and opposite. This is Newton's third law. It's a force pair. Okay, same. All right, a 70.9 kilogram woman and her 39.9 kilogram son are standing at rest on an ice rink. They push against each other for a time of 0.41 seconds, causing them to glide apart. The speed of the woman after the 0.41 second push is 3 meters per second. Assume friction is negligible during the push. Calculate the magnitude of the mother's acceleration following the push. Okay, so I know the woman started at rest because it says that they start at rest standing together. Let me get a fresh piece of paper. So I know the initial velocity of the mom is 0. I know that her final velocity is 3. I know that the time that this velocity changed, that push, was 0.41 seconds. So I can find her acceleration. I'm not going to use forces here. I'm going to use kinematics. Okay, I know that I have this equation, VF equals VI plus A times T. And if I plug in, that's 3 equals 0 plus A times 0.41. Okay, the 0 of course goes away. I divide both sides by 0.41. 3 divided by 0.41 is equal to 7.32. Calculate the magnitude of the average force the mother exerts during the push. Again, I now know her acceleration. I can find force from that because I know F net equals ma, and in the push, that's the only force because there's no friction. It says friction is negligible during the push. So if I find this net force, that will be the force that the mother experiences. So the mother's mass is 70.9. Her acceleration is 7.32. This will give me her net force. So I'm going to take my answer and I'm going to multiply it by her mass, 70.9 from the question, and this would be the average force that she experiences, 518.78 newtons. The magnitude of the average force exerted by on the son by the mother is, again, equal to, it's a force pair. She pushes on him, he pushes back on her, same amount, opposite direction. The direction of the force exerted by is, again, opposite to. This is right here, third law. Last thing, calculate the magnitude of acceleration the son experiences. You just told me he has the same force. Here's his force. Okay, we know his mass. We can find his acceleration. Same equation, F net equals ma, but this time I know the force, 518.78 equals the boy's mass this time because we want his acceleration. His mass is 39.9. We're going to solve for his acceleration. So we're just going to divide our answer here by his mass, 39.9. 0.9, and his acceleration will be 13.00. All right, hopefully that helped. There's a lot of questions here. You need to be able to do them, especially some of these that have the kinematics with that. That's what I would expect to see on your free response, things like this that have an angle, but then maybe ask you to go a step further and to calculate how far it travels in a certain amount of time or something like that. You have other examples in here with kinematics as well, so look back at those or look back at the problem set on kinematics.